Um, as a reminder, these last 2 pages are only for required for if you're going to go into BC calculus. If you are going into AB, there's no reason why you can't. This is, in my opinion, interesting stuff. So certainly welcome to do these last 2 pages. I just want you to know it is not required. If you're going into BC calculus, these problems are required because we're going to be working with these topics are expected to be prerequisite to you going into the topics in calculus. So the first thing I'm going to do is go over 17. I'm actually going to go a little bit out of order. And that's the reason is because for some reason we put this parameter problem here, this parametric equation here, and then we put a parametric graph kind of like at the end of the packet. So I wanted to group them together. So I'm actually going to do this expand and simplify and then go back and do this parametric equation problem and then next do a parametric graph equation and then we'll move on. You do not need, you will never be asked to expand and simplify straight up a problem like this. The purpose of these problems is to get you familiar again with the concept of the notation, that capital sigma means to sum, and that this number is where you start. The bottom index number is where you start inputting numbers in for n, and this is where you stop. And then this is the actual expression. So to expand this, the expectation is that you take 3n minus 6 oops, didn't mean to write that 2 there. And you are going to replace n with start at 2, then 3, then 4, and stop at 5. You're going to simplify each one of those numeric expressions, and then you are going to sum the results. Okay, so 6 minus 6 is 0. 9 minus 6 is 3, 12 minus 6 is 6, 15 minus 6 is 9, so adding 0 plus 3, 3, 3 plus 6, 9, 6, 9 plus 9, 18, right? The total sum is 18. This is a finite value, and that's because you are stopping at a finite number. So maybe that was the purpose of this one. Notice that the expression inside the summation was simply linear, right? So each time you were jumping by 3, right? Linear function, change in x, right? Change in y over change in x, whatever you want to call it. This is just, or n, right? It's just a constant change of 3 for each term. And then you started and stopped and you summed what you had. So this is the same kind of process, but notice that we put a factorial in our expression. So to remind you that what factorial means, right? If you had, for instance, 7 factorial, well, that is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. Or, of course, you could write that as 7 times 6 factorial. Or, of course, you could write it as 7 times 6 times 5 factorial, and so on and so forth. Okay. Factorials have a lot of rewriting powers. So this time we are going to start at 0 and stop at 4. So we are going to have our expression with 0, then add it with 1, add it with a 2 inside, add it with a 3, and add it with a 4. So 0 plus 1 squared over 0, in a denominator that's bad, but by definition 0 factorial is not 0. 0 factorial is equal to 1, and you're expected to know that. Then we're going to enter 1 plus 1 squared over 1 factorial right? So we're going to evaluate each one of these expressions and then sum them all. And check that I have entered 0, 1, 2, 3, and 4. So of course 0 plus 1 is 1, 1 squared is 1, and 1 over 0 factorial is 1. 1 plus 1 is 2, 2 squared is 4, divided by 1 factorial. 2 plus 1 is 3, 3 squared is 9, over 2 factorial, which is 2 times 1. 3 plus 1 is 4, 4 squared is 16, over 3 factorial, which is 3 times 2 times 1. 4 plus 1 is 5, 5 squared is 25. 4 factorial is 4 times 3, which is 12, times 2, which is 24, times 1. And we need to add those all together. So of course I need a common denominator. Add those all together, and I get 317 over 24. And no, I didn't just do that in my head. I did the problem before. But no, I had to get a common denominator of 24 in order to add those together. So I had to multiply notice I am just multiplying by 1 each time. 24 divided by 24 is 1. 24 divided by 24 is 1. 12 divided by 12 is 1. 4 divided by 4 is 1, all to get a common denominator of 24. And then I added all those numerators up and I got 317. And yes, most times that is the exact answer. I don't get a decimal approximation. I leave the answer in its rational form. Okay? So that's review of summation notation. And the things for calculus that you need to know is you need to recognize what a summation is asking you, and you need to recognize whether a summation is finite. In other words, where the stopping place, it gave you a finite number of terms to add. Or in calculus, we are often going to be dealing with infinite sums and how we deal with that. But I've got to recognize that, okay? All right. So now let's go to parametrics. So parametric equations is where in your normal, right, in normal function land, we have x and y. But remember, we have rules in function land where if you're not a function, right, some things fall apart, some theorems fall apart, and some math that we're able to do falls apart if we don't have a function. So parametrics is a way to take a graph or a relation that is not a function and turn it into multiple functions that we can then use all of our theorems based on if you are a function then. So I want you to notice that each one of these equations in terms of a third parameter t, in terms of the parameter t, each one of them is a function, right? This is a parabola that opens up and has a y-intercept of -3. 2t is a linear function with a constant slope of positive 2, right? So what happens to a particle, right, or movement? Traditionally, we think of x in terms of the parameter time being horizontal movement, and y in terms of time being a vertical movement. So what happens on a graph that has an x component, horizontal, and a y component, vertical? What happens to each point as you move horizontally in the time squared minus 3, but vertically in the time squared time just times 2? Okay, what kind of shape do I get out of that? I don't know. But how I can find that out, I don't know what that graph looks like, but how I can figure it out is by eliminating the parameter. So to eliminate the parameter, choose that third parameter that we kind of want to eliminate and isolate it. So I could choose the t in the x equation to isolate, but if I did, I'd get a plus minus situation, right? So I'm going to go here and I'm going to get this t by itself. So I'm going to take the second equation over here and I'm going to say t is equal to y over 2. Yes, divide both sides by 2, right? Then I'm going to take what t is equal to and substitute in to the first equation. So if t is equal to y over 2, then x is equal to t squared minus 3. And when I simplify that, I get an equation in terms of just x and y. And because I took Algebra 2 and I paid attention, I remember when we did the conic section, this is a parabola, but it's not a parabola that opens up or down because the y is squared. It opens either right or left. And with a positive leading coefficient, it opens to the right, and the not y-intercept, but x-intercept is negative 3. So it kind of sort of looks like that. And as you can see, that purple function is not, that purple graph is not a function. But when I write that graph, that path, with the parameter of time, I've got two equations that, separate equations, true, but they are each functions. And so I can do, there's a lot of calculus I can do on functions that I struggle to do when it is not a function. Okay, so that's the reason you need to know parametrics, is there are graphs and motion and modeling that we need to do with mathematics and do calculus upon those math models, and not all of them are functions, but sometimes I have funky ways and fancy ways of taking a scenario, a situation, a model that is not a function, turning it into a function so that I can do calculus upon it. Kind of cool, right? So that's why the next problem is actually the last problem on the summer packet. So if you're looking for this, this is number 23, but I chose to do it here because it was parametric equations, right? So it went with what I just did. So the first thing I want you to notice is that I have defined the parameter t. Now remember, this is the x-axis and this is the y-axis. There is no t-axis, and yet I'm asking you to only graph these equations on the when t is 0, and then all the way through where t is actually equal to 3. So step 1 is to consider the domain. So what is at 0 when t is equal to 0? What is x equal to? When t is equal to 0, what is y equal to? So notice these are both lines. 2t minus 1 and 3t minus 5 are both lines. So x is equal to 2 times 0 minus 1, which is negative 1. And y is 3 times 0 minus 5, which is, of course, negative 5. Plot. So when x is equal to negative 1, y is equal to negative 5, closed circle, because I was actually equal to. Now consider the end of the domain. What would the end of the domain look like? So when t is equal to 3, x is equal to something, and when t is equal to 3, y is at what position? So 2 times 3 is 6, 6 minus 1 is 5. At time 3, what is y doing? 3 times 3 is 9, 9 minus 5 is 4. Whoops, I meant to do that in red, of course. So when at, let's say, just for, nobody gave me units, but let's say 3 seconds. At 3 seconds, the particle is at the horizontal position 5 and vertical position 4. Okay. Both of these are linear. That's terrible, I missed. So, right, I have a boring old line segment. Right. I think it probably went a little unnecessary to do a line segment in parametrics, but just showing you that it can, right? There's nothing wrong with a line segment. But this also does introduce the purpose of, or being able to take a non-function and use parametrics to represent it as two separate functions is powerful, but that's not the only use of parametrics, right? There are many modeling situations where time, right, the movement, for instance, of a particle in the horizontal and vertical position is dependent upon time, and the forces acting upon vertical and horizontal may be different. One may be quadratic, one may be cubic, one may be sinusoidal, right? So our steps for graphing in parametrics is to consider the endpoints of the domain and plot them, and then look for pattern in between. Or do what we did before, which was, if you really want to know, eliminate the parameter. And if you eliminate the parameter, it can give you an idea. So even though this one didn't ask me to eliminate the parameter, let's go ahead and do that. So this time, it doesn't matter, these are easiest to do, right? So if I get t by itself in the first one, t is going to be equal to x plus 1 all divided by 2. So then y would be 3 times that t minus 5. So 3/2 x plus 3/2 minus 10 halves, yes? 5 is 10 halves. So look what this is. This is a line with a slope of 3 halves and a y-intercept of negative 7 halves. And isn't that about what my sad looking line looks like? But notice that I was given a domain in terms of time. So if I actually wanted, right? So that's why I had to actually know where these endpoints were. Cool. Oh no, dun 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 dun. Everybody's favorite subject, series. So hopefully you did some series work in pre-cal. If you were in on-level pre-cal or pre-cal 00, it was not part of your curriculum. If you were in pre-cal 30 or pre-cal HL, we did a series unit. If you're in honors pre-cal, I don't know if you were able to get to series by the end of the year or not. Nevertheless, it is series you don't have to worry about in calculus until March. So next March is about when we start dealing with series. But if you do nothing with series until then and you've never had any background information on it, the series unit's going to hit you like a ton of bricks. So hopefully doing some of this review now and then some review maybe later during the year will make that unit a little nicer on you. Because it is very, very abstract. It's very abstract. You're just plodding through it. If you feel like I really don't know what I'm doing with series, I'm just trying to follow, directions and whatever, and just like a recipe and not really sure what's when I bake it, what it's going to come out like, that's normal. It is normal to not really understand what you're doing with series or where it's going. It is a very deep concept, very abstract, as I said, and one of the reasons why BC is separate from AB, right? It's just not necessary for a lot of majors. It is very necessary for your physics, engineering, math, of course, computer science degrees. So fairly narrow, really. All right, so series converging. Firstly, you always, when you're dealing with a series, the things that you want to think about is, do I have an infinite or finite series? And if they are asking you whether your series converges or diverges, that only goes with infinite series. That question only goes with infinite series, because converging or diverging is this idea of a finite sum, right? Do you end up with a finite sum or not? Which is really crazy to think about infinitely adding numbers and being able to get to a finite sum. So, with an infinite series, it is not finite. It doesn't stop. The question that is really being asked is, with an infinite series, does the infinite sum reach a finite value that's converging, or bust out to infinity? That's diverge. Okay? See the or here? And the or here. So those of you that had me for pre-cal, you might remember my analogy, my house analogy. Right? Here's what I think of. I think of, here's a house with a roof. Right? It's my little house, my little chimney. Okay? So there's a house. I want you to think of an infinite sum as layers in the house. So when I start at 0, I have the 0 term. Then I add another term, and I add another term, and I add another term, and I add, and my sum is increasing. The idea with an infinite series that converges is that you end up adding such infinitesimally small numbers that your sum will never get out the house. The sum will always stay under the roof. Converging. Converging means the values that you are adding as you go off to infinity are so infinitesimally small, they never, 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 never go above the roof. That's converging. You're summing such small numbers that you never get out of the house. However, you have another house if you have another house where you are adding values, and here's your first term, and then you add the second term, and you add the third term, and you add the fourth term, and you add, and you keep adding, but the numbers that you're adding are big enough that they eventually bust out the house. We call that diverging. Right? So the easiest diverging, bust out the house situation is like a linear function, right? Like this one back here. Like this one. Right? Pretend, I know I stopped this at 5, but pretend I didn't stop it at 5. Pretend I had said this one is going to infinity. So you start at 0, you add 3, you add 6, you add 9. What happens if I kept going? Instead of being finite, I was infinite. I would just keep building and building and building, right? Your sum would bust out the house. This infinite sum diverges, right? And would bust out the house. Because if you look at the graph of a linear function, right? Look at the end behavior. As you go off to infinity, the graph goes off to infinity as well. I have no idea what that graph looks like. But there are some graphs, as you know, that on the right end slide off towards 0. So each one of these numbers gets smaller and smaller and smaller. The question is, do those numbers get so small, so quickly, that the sum of all those values are going to stay in your house? Or will they bust out? They might not bust out as dramatically as a linear function would bust out, but the question is, I can clearly see that a function that goes off to infinity, that behavior is definitely going to bust out the house. just because your function approaches 0, sometimes you bust out. Do you converge or you do diverge? I don't know. So I need to know tests. Do I know or do I not know? Answer. First, you have to run tests on your series. The first test that you always run is the nth term test. If your terms as you go to infinity don't go to 0, as n goes to infinity, if your terms don't go to 0, you are definitely going to bust out the house, right? You have a linear function, you have a parabola that opens up, you have a parabola even that opens down, that's going to negative infinity. You have a linear function with a negative slope. Which is why it's really nice to know about end behavior of certain functions, because you don't have to really run the test, right? You're just like, hey, this swooshes off to infinity, this goes off to infinity, definitely going to bust out the house. So that's always the first thing you think of, the nth term test. If, when n goes into infinity, your terms don't go to 0, then you diverge. If your terms do go to 0, in other words, you're asymptotic as you go to 0, right? You're sliding off to 0. So if your terms do go to 0, then you say to yourself, self, which of these tests should I use? Is my series geometric? Is my series a p-series? Is my series...
Sorry, I couldn't quite hear you. Could you please repeat what you said?
Is my series similar to either a p-series or a geometric series? Is the ratio test appropriate? Don't worry, I'll go over these. Is the alternating series test appropriate? And there are others, but those are our most famous ones. Okay, those are the ones that are used most often by AP. So the first thing that is necessary is, of course, do you know what all of these tests say, right? And it's kind of like, right? Kind of like in today's world, unfortunately, we do know about taking a test, are you positive or negative, right? And what do you do with those results? So we are testing a geometric series to see if geometric series, will it converge or diverge by the results of the test. A p-series test, if I have a p-series, run the test on it, the results of the test will tell me converge or diverge. So this summer packet only is touching on a few of the series that you really need to focus on. Okay, so I'm going to erase this while I work on, well, no, I won't erase this. I will just do the first problems. So A, I need to recognize, and this is part of what pre-cal is for, this is geometric. A geometric series has a common ratio. So A is a geometric series Since A is a geometric series, I need to run the convergent tests. If the common ratio is strictly less than 1, then the geometric series passes the convergence test and you converge. Otherwise, diverge. So what is my common ratio in A? ratios is another way to say fraction, right? Since in A, the absolute value of 3/2 is greater than 1, my geometric series fails the convergence test and therefore diverges. Okay, so if you were to expand this sum and get 3/2 to the 0 plus 3/2 to the first plus 3/2 to the second, even though these terms go to 0, the sum will bust out the house, right? The sum will bust out the house. Now look at B. B is almost a p-series. Almost. A p-series is always of the form 1 over n to some power. And notice that my series is really, really close to 1 over n to the 4th. So, since I'm super, super close, I'm going to choose 1 over n to the 4th to compare. Then I'm going to tell you what I know about 1 over n to the 4th. By the p-series test, 1 over n to the 4th stays in the house. Because by the p-series test, when p is strictly less than 1, when p is strictly greater than 1, a p-series will converge. Now remember, I don't actually have a p-series, right? I only have something that is really, really simple, really, really similar to a p-series. But draw a little graph here. One over n to the 4th falls towards 0. And by the p-series test, I know it falls quickly enough so that the sum stays in the house. Since it says position. Since 1 over n to the 4th is always bigger than or equal to 1 over n to the 4th plus 1, right? And think about that for a second. Your denominator is bigger. So for instance, if this is 1 over 1,000, this is 1 over 1,001, right? If the denominator is bigger, the overall ratio is smaller. That means that 1 over n to the 4th plus 1 is under 1 over n to the 4th. And if you know 1 over n to the 4th has small, way, way, way small numbers that will keep the sum in the house, then by the direct comparison test, converges to. Okay. So remember, when you're doing a comparison test, and we learned 2 of them last year, direct and limit, but when you're doing a comparison test, you have to choose a very, very similarly behaving function. We called this a cousin, right? 1 over n to the fourth plus 1 is a cousin. I'm sorry, 1 over n to the fourth is a cousin to 1 over n to the fourth plus 1. And to use the direct comparison test, I had to show what I know about the cousin, and then that I know my series lies under the cousin if my cousin converged, and lied above my cousin if my cousin diverged. All right, both of these are a little tricky. Firstly, if you look at D is the reason we asked you to practice expanding summation notation, because this time you have to recognize the summation notation and then deal with your converging or diverging. This one is already in summation notation. Oh gosh, I have to go back to the previous page because I realized I just forgot there was a key part of the question I forgot to answer. I explained why A converged or diverged, right? So I explained that this sum diverged, and I explained why. If the sum diverges, I can't possibly tell you what the sum is. I don't reach a finite value. I go on forever. If I have a p-series, right, the p-series converges, and I explained why it converges, right? All this work I did explained why. But if it converges, I'm supposed to give the sum if possible. So let me give you the fine print on that. If you have a series that converges, the only kind of series that you can give me a value for, a value of an infinite sum, is geometric. This geometric series diverged, so it's not possible to give the sum because it diverges. This p-series converges, but it's still not possible to give you the sum to which it converges, because the only way that is possible is if you have a converging geometric series. Then I can give the sum. So I wanted to talk about that before I did these two problems. So I'm going to do C first and then D. Now, from experience and wisdom, not because I was born with this knowledge, when I see a series, an infinite series, and I'm asked to tell whether this infinite series converges or diverges, and it's clearly not geometric, I hope you can see it's not geometric, and it's way too messy to be a p-series. Well, a p-series has to have a 1 in the numerator. This certainly does not have a 1. If I see a whole bunch of powers, or factorials, or both, I think to myself, maybe run the ratio test. So let me refresh you on the ratio test. The ratio test means you have to run a limit as the terms go off to infinity of the absolute value of a ratio, and that if that ratio is less than 1, you get converging. If that ratio is greater than 1, you get diverging. If that ratio is equal to 1, the ratio test is inconclusive and you have to go find another test. Okay? And the ratio is subsequent term to previous term. Okay. Don't worry if that, you can look that up. It's not that big of a deal. You don't need it right now anyway, because let me give you a foreshadowing. This is not going to take the ratio test. But you might be fooled into wasting time trying to do the ratio test. Let me tell you how, again, my experience made me think about doing maybe the ratio test, and then I decided not. And it's my pre-cal knowledge, my algebra 2 knowledge. I said to myself, there are no factorials in here. This is an n squared and an n to the first, meaning this numerator is an n cubed. This denominator is an n cubed, and I'm going off to infinity. These terms approach 1. And it is analogous to thinking about a horizontal asymptote at 1. The terms do not go to 0. Remember the directions asked you to explain why. I just did. The terms don't go to 0. That's always number 1. Look at your terms and use some of your algebra background to say, hey, I'm always going off to infinity. Is this a linear function? Shoots off to infinity. Is it a parabola? Shoots off to infinity. Oh, this is a rational function. It does level off, but it levels off at 1, not 0. So these terms, even though I'm not really talking about a graph, it still helps me think about all of these terms do not go to 0. All right, so that was the twist on, so this one was a twistier problem. D is also a twist, because firstly, they didn't give you summation notation, and I need it. Secondly, you do have to recognize that these dots mean you're going to infinity. But I'm not quite sure how I start, and I'm not quite sure what my expression is in here. I really am looking at, I do recognize my pattern here. It looks like I've got, for the most part, 3's in the numerator and 7's in the denominator. I really, really, really would like this to be geometric. And if it's geometric, I really, really would like to write fraction to the n, right? Now this 1 really bothers me here, but I do notice that most of the time I have a 3 and a 7 to the n. So I'd really like to be able to write this as 3 7s to the n. But if I start this at 0 and check, 3 7s to the 0 is 1, not 1 7th. Also, when I make n equal to 1, I get 3 7ths. But notice, this is 3 to the first over 7 squared. This is 3 to the second over 7 cubed. My powers don't match, and if I'm geometric, my powers have to match. Ugh. All right, I cry for a minute, and then I say, okay, so what can I do? All right. Let me do a little rewrite here. What if I want this to be 3 to the first over 7 to the first? That's not quite what I have here. I have an extra 7. And how about the next one? Right, the next one is 3 squared. I really would like it to be over 7 squared, but it actually is over 7 cubed, so it has an extra 7. Oh, wait a start. I'm starting to feel a little bit better. I really want this to be 7 cubed, but there's an extra 7. Oh, wait a second. Couldn't I write this as Couldn't I do that? Now, wait a second. How about I do this? Instead of, so how about I do right? Every time I've got an extra what? Every time my fraction is messed up by this division by 7 or multiplying by 1/7. So how about I just say 1/7 times my 3 to the 7. Now let's check it. Does that work? When I plug in 0 for n, 3 over 7 to the 0 is 1. 1 times 1/7 is 1/7. How about n to the 1? 3 to the 7th to the 1st is 3 to the 7th times 1/7 is 3 over 7 squared. What's that? Oh. Boo. Boo. Oh, maybe I should do this. What happens now? When you put in a 1 here, negative 3/7 to the 1st is negative 3/7 times 1/7 is negative. How about when n is equal to 2? When n is equal to 2, negative 3/7 squared is positive 3 squared over positive 7 squared times 1/7 means I've got 3 squared over 7, everybody's positive. Yay! Turn that frown upside down. I forgot what I was doing. Oh, right. I have to say, this series is geometric with a common ratio. If it's less than 1, I get convergence. If it's greater than or equal to 1, I get divergence. My common ratio is negative 3/7, but the absolute value of negative 3/7 is less than 1. Therefore, converge by the geo-series test. You've done a lot of work, you've done a lot of good work, and you've got the right answer, but you still don't have full credit. Think about the directions again. What did the directions tell us to do? Explain why. We said if the series converged, we explained why it converged. We have to give the sum if possible. It's only possible if you have a geometric convergent series, which is what we got. So, since we have a convergent geometric series, the sum of an infinite converging geometric series is S for infinite sum. The first term divided by 1 minus the common ratio. So look at what my first term is. It's a fraction, so I'm going to put it out front, times 1 over 1 minus the common ratio. No absolute value, just the common ratio itself. So what does that equal? 1/7 times 1 over 1 plus 3/7, which is 10/7, which is 1/7 times 7 over 10. Cancel out those. And I get 1/7 1/10. OMG. Right? Kind of crazy. So, series again isn't something you really have to concern yourself with for a while, but it is why BC is BC and not AB. You do have to not only know series, you have to know when these series converge and diverge and which tests to run, and then we have to do calculus with these series. Okay? It'll be good. You'll be fine. I'll get you through it, I promise. All right. Take care, and I will see you on the next test.